Welcome to the next session on ANSYS Workbench tutorials. In this session, we will analyze the water bottle for its bursting pressure. We will start by double-clicking on Explicit Dynamics module. Next, we'll go to Engineering Data and double-click. Here we'll go to Engineering Data Sources. Then we will go for Explicit Materials and double-click. We will analyze the bottle for three different materials. One is aluminium, second is copper, and the third is stainless steel. So first we will look for aluminium. We'll bookmark here. Next we'll go for copper. And add over here. And the last one is stainless steel. We'll click on this plus sign. Once we have added all the three materials, we'll click on Engineering Data Sources again. So you can see here, these are the three materials which we have chosen. Then we'll go to Project and Update Project. Next, I'll go to Geometry, right click and import the geometry. Since I already have the geometry with me, I'll directly import. Then I'll go to Model and double click. Next, we'll go to Geometry and click on this plus sign beside it. We'll select the parts and we'll change the material. First, we'll change to aluminium. Next, we'll go to Mesh and update the mesh with the default size itself. Now we'll apply the boundary condition. First, we'll go to Analysis Settings. Here we have to give the time. So I'll give this end time as 0.001 second. Then I'll go to Explicit Dynamics A5. Here I'll right click and insert fixed support at the bottom of this bottle. Apply. Now for applying the rest of the boundary conditions, you need to hide this cap for some time. So I'll just select this one, right click and hide body. Then I'll select the surface. So let's select face option, select this one. Right click, insert. Okay, so you need to go to Explicit Dynamics A5 again. Right click, insert, force. I need to change the vector to component. So I'll select here, change it to component. Now we need to set the direction. Just hold the body parallel to this axis. You can see this is the y-axis. So here we will be giving a force of minus 50 Newton. Then I'll right click here again and insert pressure, which will be the bursting pressure on this bottle. Now I have tested for various values. For aluminium, if you test at a pressure of 30 megapascal, you will see the bottle is completely safe. But if you change the pressure to 35 megapascal, there will be a bursting effect. So for aluminium, I'll show you both. And then for copper and stainless steel, I'll show you one of the analysis and the other I'll give you the value. You can check for yourself what kind of results you're getting. So for aluminium, you will start with the pressure. Let's first select the geometry. You need to select the geometry from inside here. Click on apply. I will first give this value of pressure as 30 megapascal. I'll now go to solution and right click, insert deformation total. I also want to see the deformation directional. If you want to see along the x-axis, you can select here, go to x-axis, go to orientation, this is along the x-axis. Then I'll go to solution, right click, insert strain equivalent, and also I will insert the stress equivalent. Then I'll go to solution and solve. Now since this is a time-based analysis, this will take some time. You need to leave it to give you the solution. So now you can see the solution is obtained. What we'll do is unsuppress this cap here. So we will show this body. We have hidden the body. Now we'll show it. Then we'll go for total deformation. You can see here there is a maximum deformation of 3.53 mm total deformation value. You can animate and check this result. You can see there is no busting, but there is definitely a permanent deformation in this body as shown in this graph. Next, we will go for the directional deformation along the x-axis. This is 3.25 mm maximum. You can again animate and check this result. This is the zone where it is maximum and this side it is minimum. Then we'll go for strain. Maximum strain is 0.0039, which is again a very less value. And the stress value is 285.54 megapascal. So here you can see again this is the elastic zone and then there is a plastic zone, which means the deformation is definitely going to be plastic type, which means it is permanent deformation. So once you have obtained this, you can now change this value of pressure. I told you at 30 megapascal there is no bursting effect seen, but if I want to see the bursting effect, I just need to change this to 35 megapascal and solve once again. The solution is obtained. We'll click on total deformation. You can see here this bursting effect. The maximum deformation is 250.99 mm. We'll just click on the play button and see how the bursting happens. You can see there is a total bursting because of this internal pressure on the bottle. Next, we'll go for directional deformation. You can see here the value is 242.95 mm maximum along the x-axis. Again, you can animate and see the pattern of animation will be the same, only the colors over here that you see are going to be different. Then we'll go for elastic strain. The maximum value is 0.004 and the stress is 290 megapascal. So you can see from 285 to 290 megapascal makes such a great difference in the result that is going to occur on the bottle. So this is all about aluminium. Now we will change the material to copper for the lid as well as the body of the bottle. Now here there are two values. One is 30 megapascal at which you will see a complete bursting of the bottle, and if I give 20 megapascal pressure, there will be a normal deformation seen. Now for copper I am solving for 20 megapascal. We go to solution and solve. Now let's see the result. We'll click on total deformation first. Now you must be wondering that the name of the video is bursting pressure on this bottle, but I'm still choosing to go for 20 megapascal wherein the bottle is not bursting. It's just that I want to show you this value, and at 30 megapascal I think you can just change the value and you can get the reading. So we will go for total deformation. Here the maximum value is 8.0339 mm. You can animate and check this video. You can see where the color is red. This is going to be the maximum deformation. Then we'll go for directional deformation. The value is 7.8866 mm along the x-axis. Again, the value is max here. Then we'll go for strain. It is 0.00225 max. Again, you can see where it is max. This color red will show you maximum value, and the rest of the colors are showing you lesser than the maximum value. If you want to see them, you can just click this probe option, take the probe over these points, and you can just check what is the value here. If you don't want to use the probe option, just click on probe once again. Then we'll go to equivalent stress. Value is 275.79 megapascal. You can see where it is maximum. The rest of the places it is going to be lesser than that value. You can again animate and check this result. If you change this value of pressure from 20 to 30, you will see a complete bursting effect of this copper bottle. Now we will go to the next material, which is stainless steel. So I change the lid and the body both to stainless steel. Then we'll go to pressure. Now again I'm giving you two values of pressure. If I use 75 megapascal, I will not see any bursting effect. But if I use the pressure as 80 megapascal, there is a complete bursting of this bottle. So now, as the name suggests, we will take up the value as 80 megapascal. We'll go to solution and solve. We will first go to total deformation. You can see here there is a complete bursting of this bottle. The value of deformation max is 153.54 mm. You can run and see this video. You can animate. Then we go for directional deformation. Maximum is 143.31 mm along the x-axis. You can animate and see where it is going to be the max. You can see here this side it is maximum, red. Then we go for the value of strain. It is 0.0052 and the value of stress is 1000 megapascal, which means definitely your body has failed, because 1000 is not the value of tensile ultimate strength of steel. So that's why the body has definitely failed. You can see here it has failed here. If you check the graph, it has failed at this point somewhere more than 500, and then there is a complete plastic deformation, and this is going so flat, which means that there is a permanent deformation in this body, and here the deformation is of bursting type. Now if you do the same analysis using static structural, you won't see this bursting effect. You will only see the stress increasing, you will see the deformation. If you want to see the complete bursting of this material, you need to use this module of explicit dynamics. So with this, I end the session. I hope you have understood the comparative analysis of a bottle which is made of three different material, and it is subjected to different type of internal loading. Only then you will be able to see a bursting pressure. Now if you analyze for 20 megapascal, say, for all the three bottles, that is of three different material, you will not see a bursting in any three of them, because the minimum value where the bursting was not taking place was for copper was 20 megapascal. So if you apply 20 megapascal or 10 megapascal over the bottle surface from inside, irrespective of the three material, your bottle is going to remain safe. If you ask me what is the safe value, then it is say 10 megapascal, 5 megapascal or 20 megapascal. But the moment you change it to 30 megapascal, it will burst open for copper. For aluminium, it will still be safe. For steel, it will be safe. But if you shift it to 35 megapascal, again for aluminium and copper, both there will be a bursting effect. But for steel, it will be safe. And if you go for 80 megapascal, then all the three materials are going to show a failure. So that's the cumulative result for this analysis. If you have any doubt, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.